the reason why it's as useful to physicists as it is has to do with what's known as the conservation of momentum. Now, you've likely heard of conservation laws before in chemistry or maybe some of your other science courses. The first thing I want to point out is that in general, a conservation law just follows the general statement: blank cannot be created or destroyed, only transferred, or sometimes only change form, something like that. But whatever the thing you're talking about, if it follows a conservation law, you cannot create or destroy it. You can only move it somewhere else, transfer it to some other object, turn it into some other form of the same thing, but you just literally cannot gain more or less in terms of this scope of the universe, right? You can't get, the universe will never have more or less of whatever this thing is. So momentum is a property that follows the conservation law. So momentum cannot be created or destroyed, only transferred. So this maybe will make things a little bit clearer. Why have we been calculating momentum? Why have we been looking at impulses, etc.? Because if there's a collision and one object loses momentum, then the other object has to gain that momentum. All right, that's what is meant by conservation law. So I had a hard time defining momentum for you guys. I was like, it's mass in motion. It's like a property that objects. A better way to say it now that we can discuss this is it's a property that moving objects have. And when we analyze collisions, we know that whatever amount of momentum that we calculated to begin with, we have to have that amount at the end. So that allows us to analyze or calculate like what final velocities do we have to have so that the momentum didn't change. So that's why it's so important. It's very hard to define because it's basically a quantity that can't go away. You can transfer it to another object, but overall you can't have any more or less than you started with. And that's really powerful, at least mathematically, which I'll show you guys in a second. Really quickly, just some of the other conservation laws that you either have discussed previously or we will discuss in this course. There would be things like the conservation of mass, if you remember from chemistry. If you do like some kind of chemical reaction, however many, grams of some substance you had in the beginning, even if it becomes some new compound or something, you still have to have the same amount of grams afterwards. You can't just destroy mass, okay? It might become some other element or compound, whatever, but you have to have the same number of grams, amount of grams as you had prior to that reaction as you had afterwards. Energy is another one. So energy, we haven't discussed that yet, but a lot of people generally know the statement, energy cannot be created or destroyed, only change form, transferred, etc. And electric charge. Okay, electric charge is not one most people know about, but static electricity. Anytime you've ever gotten a shock from something, however many electrons you just lost, the other object gained, or vice versa. You can't just have electrons just pop out of existence. That's what electric shock is. You are transferring a certain amount, or a certain amount is being transferred to you. But anyway, that's not important. The important part right now is that whatever that transfer is, whatever one object loses, the other object gains. That goes the same for energy, the same for momentum. Anything that's a conservation law follows this kind of principle. All right, so to kind of simplify it, I like to use this example. Let's assume you have person A and person B. This is going to be a very simplistic example, so if you kind of already know where I'm going with this and you want to skip ahead, by all means, go ahead. But if person A has $30 and they hand $30 to person B, we want to just kind of analyze this analogy to see what's going on here. So if we just keep track of what's going on, well, before anything happens, person A had $30, person B had none, so collectively, total, both of these people together, assuming we're going to ignore bank accounts and stuff, if this is the only money that exists, they both had $30. Okay, A had 30, B had 0, so together they had $30. Afterwards, after person A transfers their money to person B, well, now person A has $0 because they gave the money away. B now has the $30, but collectively they didn't make any more money. They still only have $30 between them. So we've got person A, person B, and then the total of those two together. If we just look at the change in the amount of money they each experienced, well, A lost $30, they gave it away. B gained $30 because they received it, but the total change is 0 because they still only have $30. And that's the important thing. Okay, momentum follows a very similar ideology. I should say law. It follows a very similar physical law. So whatever momentum one object loses, the other object gains. So if you know how much momentum one object loses in like a collision, then you immediately know how much the other one gained, and now we can start to do some calculations. So that's the basic idea. We could talk about the individual people, right? They did individually lose some or gain some amount of money. But if there's only two people, whatever one lost, the other had to have gained. There's no third option for that money to go to. If there's a collision between two objects, there'd be no third object for that momentum to maybe have gone into. All right, so this last part here, as I said, that kind of shows that conservation part. There's no change. There's no change in total. Yes, the individual objects might have experienced the change, but overall, there is no change, right? You still have 30 before, you had 30 after, no change. That's kind of that conservation piece. All right, so let's look at it a little bit mathematically, just so we kind of understand what's going on here. All right, in general, it's as simple as this. The initial momentum that you had prior to the collision must equal the final momentum in total after the collision. Doesn't matter how many objects you have, doesn't matter what their momentums are, but whatever the total amount of momentum you started with must be the total amount of momentum that every object collectively added together ends with. Okay, in the next video, I'm going to go over several different examples, but if you've picked up from this that whatever amount of momentum all the objects collectively have together must be the same afterwards, even if they transferred a bunch of momentum between one another, then you're in a pretty good position. We'll take a look at the math in the second one, and that'll probably clarify things quite a bit.